Hello. In this video, I'll explain how the deformable vehicles in Unreal Engine 5's City Sample are implemented. I've spent over 2 months studying the code to understand how it works. While I've grasped a good portion of it, I still don't fully understand everything. Also, I'm not an Unreal Engine expert, so there may be some mistakes in my explanations. I've also written down what I've learned in a Google document, which you can find linked in the video description. As you can see, the City Sample vehicle deforms or breaks when it collides with objects. However, if you observe closely, you'll notice several distinct patterns. The destruction processes implemented in the City Sample vehicle mainly include breaking the door lock, breaking the trunk lock, breaking the hood lock, breaking the glass, and breaking the front grille. The deformation processes include trunk deformation, hood deformation, door denting, and frame deformation. Destruction and deformation are implemented using different approaches. In this video, I'll first explain the deformation process. Understanding control rig is essential for grasping the implementation. I'll now explain how control rig manipulates bones. If you're already familiar with control rig, feel free to skip this part. First, let's open CR Frame Destructible. This is where most of the deformation logic is implemented. Next, let's change the preview mesh to the police car. Open the Preview Scene Settings tab and set the preview mesh to SKM Proxy VCar Vehicle 13. You can use any preview mesh, but for consistency, I'll be using the police car throughout this video. When you open the control rig, you'll see a tab called Rig Hierarchy. This tab displays the bone hierarchy. One common misunderstanding for beginners is that the bones in the control rig are not directly tied to the bones of the skeletal mesh. Control rig controls its own internal set of bones. Therefore, to control a skeletal mesh's bones, you need to recreate the same names and structure inside the control rig. In other words, the bone hierarchy you see in the control rig simply mirrors the names and structure of the bones from the skeletal mesh you intend to deform. However, as it stands, the skeletal mesh bones and the control rig bones are not linked, so moving the bones in the control rig won't affect the skeletal mesh. To fix this, we need to map the skeletal mesh bones to the control rig bones. The mapping links bones with the same name between the two. By doing this, the current transforms, position and rotation of the skeletal mesh bones are transferred to the corresponding control rig bones. After performing operations and deformations inside the control rig, the updated transforms are then written back to the skeletal mesh bones, because mapping is done by bone name. Even if the control rig's internal hierarchy differs from that of the skeletal mesh, bones with matching names can still be mapped correctly. It is also common in control rig to introduce virtual bones, bones that do not exist in the original skeletal mesh, to help stabilize or assist IK calculations. As a result, the bone hierarchy within the control rig tends to be more complex than that of the skeletal mesh. Now let's try deforming the preview mesh. The yellow spheres are control handles, called controls. By moving them, you can deform the mesh. As you can see, the deformation of the vehicle is achieved by moving the controls. Controls are placed at the rear, front, top, and sides of the vehicle, allowing deformation to occur no matter where the vehicle is hit. Right now, we're moving the controls manually, but during runtime, they are moved as a result of collisions with objects. Now, let's go over the concept behind how this is implemented. In City Sample, the skeletal mesh used to detect bone position and rotation changes via physics simulation is separated from the skeletal mesh used to display the deformation. Each skeletal mesh is mapped as either the input or output of the control rig. The skeletal mesh for physics simulation has a simple structure. The control rig places controls at the collision detection bone's position, enabling the controls to be moved indirectly when the corresponding bones are displaced by collisions with objects. The control rig bones include several virtual bones which are used as helpers, for example, to stabilize IK calculations. In the control rig, the bone poses are calculated so that the bones can follow the controls, which are moved by collisions with objects. As a result, the bones in the control rig are deformed. Then, the poses of these deformed control rig bones are applied to the skeletal mesh bones through output mapping. This is how the city sample vehicle deforms the vehicle body in response to collisions. So far, I have explained the conceptual overview of the implementation. From here, I will explain the concrete implementation details. The overall architecture of the city sample vehicle deformation system is illustrated in the diagram. First, the root skeletal mesh, which has a physics asset, detects collisions with objects. Because the physics asset is being simulated, the corresponding bones move as a result. However, these bones do not directly deform the mesh. Instead, they are referenced as inputs by the control rig. The control rig takes the moved input bones and calculates the deformed poses of the various bones distributed throughout the vehicle body, using techniques like IK. Once the deformation process is complete, the final poses of the deformed vehicle bones are output to the proxy skeletal mesh. The proxy skeletal mesh then applies these deformed bone poses to both the interior skeletal mesh and the exterior skeletal mesh. At this point, you're probably not sure what all of this means. Let's go through each step one by one. First, open the blueprint with the _sandbox suffix. In this example, I'll be using the police car. When you open it, you'll see that a skeletal mesh is used as the root component. This is the root skeletal mesh. This skeletal mesh contains the physics asset and the basic skeleton. Let's open the physics asset and take a look. These are the bones and the physics asset of the root skeletal mesh. You'll notice that the bone structure is quite simple. That's because the bones of the root skeletal mesh don't actually deform the mesh, so there's no need for a complex bone setup. The main role of these bones is to act as sensors for detecting collisions with objects. It's important to note that the root skeletal mesh doesn't have any visible mesh. It's just used for collision detection. How does the control rig detect when these bones change position as a result of collisions with objects? To find out, let's open the BP vehicle-based deformable blueprint. This blueprint handles both the destruction and deformation of the vehicle. So if you want to gain a deeper understanding of the implementation, I recommend focusing on this blueprint. When you open this blueprint, you'll see that it contains a huge number of events and functions. It took me 2 months to read through all of them. For now, let's take a look at the on-pre-initialize CR frame destructible event handler. After that, open the control rig pre-initialize event graph. In this event graph, the inputs and outputs for the control rig are set up. It also configures the vehicle type. There's a node here called Add Mapped Skeletal Mesh. This node specifies the skeletal mesh component that will receive the bone poses controlled by the control rig. If you look at the blueprint, you'll see that SKM proxy is set as the output target. This corresponds to this part of the architecture diagram. The bone poses deformed by the control rig are applied to SKM proxy. Let's open SKM proxy here. While the root skeletal mesh only had a simple bone structure, the proxy skeletal mesh has a much more complex one. This is because a large number of bones are needed to deform the mesh naturally. The control rig deforms the vehicle by bending these bones. If you look at the hood, you'll see that the bones are set up to allow for natural-looking deformation. Let's go back to the blueprint from earlier and open the Map Physics Bones to Control Rig Controllers event graph. This graph sets up the bone poses that will be input to the control rig. Take a look at the Make Mapped Element node. This node specifies the root skeletal mesh as the component containing the source bones, and sets the direction to input, so that when the bones of the root skeletal mesh move, their poses are fed into the control rig. This allows the control rig to calculate, using IK, how much to move the bones of the proxy skeletal mesh. This corresponds to this part of the architecture diagram. It's not a problem if the input and output bones of the control rig have different structures. I don't fully understand all the details myself, but as far as I can tell, when a bone with a certain name is given as an input, the control rig applies that pose to its own virtual bone with the same name. Then, the control rig deforms the bone with the same name in the proxy skeletal mesh to match the transformed virtual bone. In this way, control rig associates bones based on their names, which means you can reuse the same control rig with different skeletal meshes as long as they share the same structure. In the city sample, there are over a dozen different vehicles, but they all use the same bone structure. Of course, the skeletons may look different depending on the vehicle type, but the naming conventions are standardized. Next, I'll explain the interior skeletal mesh and exterior skeletal mesh. You might be wondering why there's a proxy skeletal mesh in the first place. The reason is that both the interior and exterior skeletons need to be deformed in exactly the same way at the same time. Let's take a look at the exterior mesh. If you view it from the inside of the car, you'll notice that it isn't rendered. This is called backface culling. In 3D graphics, a mesh has front and back faces, and the back faces are not rendered when viewed from behind. In the city sample vehicle models, both the interior and exterior meshes are combined so that there are no back faces. This ensures the model is rendered correctly from any angle. Because of this, for example, when the door lock is broken and the door opens, the doors on both the interior and exterior meshes need to move together in exactly the same way. Unreal Engine provides a feature for applying the same bone poses to multiple skeletal meshes. This is called leader pose, and you can set it using the leader pose component node. To see this in action, let's go back to the blueprint and open the Set Master Pose function. Here, you'll see that the Set Leader Pose component node is used to set SKM proxy as the leader pose component so that its pose is applied to both SKM exterior and SKM frame destructible. What I've explained so far is the overall concept behind the deformation system. Destruction events, such as the trunk opening after an impact, are implemented using a completely different approach. I'll cover that in the next video. I don't think it's easy to fully understand everything just by watching this video once. The city sample vehicle implementation is extremely complex, and because destruction and deformation each use different systems, it's difficult to explain everything concisely. Even while writing the documentation, I sometimes get confused by how complicated it is. Structuring the content in a way that makes it easy to understand, both in the document and the video, has been a real challenge, and I imagine it might feel overwhelming if this is your first time seeing it. If you have any questions, feel free to leave a comment. Thank you for watching.